I'm Pajmahani, and this is the second lab for physics. The purpose of this lab is to explore the motion of a free-falling object, excluding drag and including drag. As the object falls, which in this model is a loose paper ball, the object's velocity increases. However, as the velocity increases, so does the force of drag opposing the motion of the object. By observing a real-world system and then modeling it both with and without the drag, we're better able to understand the effects of the forces of gravity and drag on a free-falling object. The relevant formulas are the force of gravity, the drag force, the position update formula, and the velocity update formula. The system is the paper ball, and the surroundings are the Earth and the atmosphere. The initial conditions are listed. The ball's mass will be used to calculate the force of gravity, and the ball's diameter can be used to find surface area, and then can be used for drag. So here's my tracker, here's my GlowScript code, and here are the results for GlowScript. And this is the overall data. So this is mapping my different results. So as time passes, the change in position becomes larger for the same intervals of time, and thus the velocity of the object is increasing as time increases. Comparing the two GlowScript models to the data found by tracker for the observed system, it is clear that the model including drag more accurately represents the observed system. In the model without drag, there is a constant rate of change of velocity, which in the real world is inaccurate, as it does not account for the force of drag opposing the direction of the velocity of the ball. In the model with drag, the velocity increases at a decreasing rate, which is a result of the force of drag opposing the direction of motion and being proportional to the square velocity. The drag coefficient was found to be b is equal to 0.00555. At this value, the final position of the ball was found to be nearly identical to the final position of the ball observed in the system in real life. In addition, the position versus time graph shows that the observed data and modeled data with drag are nearly overlaying. The primary source of error is the ball was not released with 0 meters a second. The formula for drag was also assumed to be a little off, just to simplify things, and the tracker application maybe didn't account for everything, such as, I don't know, a slight breeze or something like that. The paper ball is not perfectly symmetric. There's a lot of things that could have gone wrong. So what does it mean? A model without drag has a constantly increasing velocity that will continue to have the same rate of change velocity. The model including drag has a velocity that's increasing at a decreasing rate due to the force of drag. The force of drag will increase in the opposite direction of the ball's motion, eventually reaching equilibrium with the force of gravity and thus reaching its terminal velocity. What if the object was initially thrown downward and the ball's terminal velocity would not change? Then, even if the ball was thrown faster than the terminal velocity of the ball, it would then slow down as the force of drag would be greater than the force of gravity until it reaches the terminal velocity. Terminal velocity is the maximum free fall velocity of an object, and is calculated using the formula v is equal to the square root of 2mg over PAC, which does not include initial velocity and thus does not affect the terminal velocity, only the time it takes to reach terminal velocity. Conclusion. In a free fall system, an object will experience both the force of gravity and the force of drag, and thus will eventually reach a terminal velocity. Thank you.